Okay, so we're going to look at a problem on page 115. Going to do it slightly differently to what's in the textbook. Cast my eye across to the solution on the textbook. I'm going to do it slightly different because they're using what's called the modulus section, and I don't think that particularly helps us. So the equation we'll be using is where we've got this beam. It's potentially experiencing a maximum bending moment of 5 kilonewton meters. You would get this result from we look at a beam, we put a load on top, and then we'll plot a shear force diagram. And that would look something like this. And then we'd plot a bending moment diagram, and that will be the integral of the shear force diagram, so it'll look like that. Well, this value here is probably the problem, kind of problem we'd be looking at. That would be where the maximum M is, so my M max, and that could be, say, my 5 kilonewton meter value. Alright, so if you're wondering where these bending moment values are coming from, they're coming from your bending moment diagram. So the issue is that I've now got this sort of plank of wood, bit of timber, and I've got to decide of whether I'm going to lay this timber so that it's sort of standing up. So we've got 100 millimeters standing up like that, or perhaps we should lay it more kind of flat so that the depth of this is going to be 60 millimeters. Right, so let's consider the first case where we're going to assume that we're going to have the wood so that it's upright. So we've got 100 millimeters there, and that's the part A they're doing. So part A, they want you to calculate I XX. So what's important here is looking at this subscript term XX. This is referring to this axis. It's the XX axis. Okay, so we are imagining that this is my neutral axis, that my load is coming from above, and it's causing the beam to bend. Okay, so this is my depth. And this is my breadth. So I'm going to use the formula to find what the second moment of area is. B, breadth, times depth to the power 3 divided by 12. And so the breadth is 60 millimeters. The depth is 100 millimeters to the power 3. Divide that by 12 and we get the result of 5 times 10 to the 6 millimeters to the power 4. So the next stage is they want me to find, for this condition, and we'll call this therefore, if we've used subscript XX for this sort of setup, we'll call this therefore stress XX. Okay, and I'm going to use the formula from the bending moment equation, the flexorial equation, m over I times by y. So it's slightly different in the book. So I'm looking for, it says the maximum stress. So you can see that my I is now fixed, my m is fixed, but my y could be any value inside this beam, and we're going to choose y to be always pointing downwards in my convention, and I'll be flipping the m value depending on whether it's sagging, which is in this case, or a hogging case. So if y is pointing downwards, we're looking for the maximum. The maximum doesn't imply whether it's positive or negative, but we'll take the positive because we're going to get either result. So you can see that if we go y going all the way down to the bottom, well, that would be 50 millimeters. If I take y to be going to the top, we're going to get minus 50 millimeters. So either way, I can see the maximum stress that's going to be caused will be either a tensile stress or a compressive stress, and they have the same value, which is what you expect for a symmetrical cross-section. So let's put that in. We're going to then take our 5 kilonewton meters. I'm going to convert everything into I'm going to convert everything into meters because here we've got Newton meters, so we're working meters, I think. So 5,000 Newton meters, that's my m. Now I've got my I value, so I've got 5 times 10 to the 6, and that's in millimeters to the power of 4. Okay, so to convert that into meters to the power of 4, I need to divide by 1,000 once, then again, then again, then again. So that's 4 times. So basically we're dropping the indices by 3 4 times. 3 times 4 is 12. So multiply this by 1 times 10 to the minus 12, which is kind of nice because you're going to see that your 6 is going to become minus 6. And then let's put in the y value, and as I said, it doesn't matter if I go up or down, I'm going to get 50 millimeters. So 50, going to work in SI units. So that's going to be 50 times 10 to the minus 3. Convert millimeters into meters, we just divide by 1,000 once. Put those values in, and we're going to get the result of 50 times 10 to the 6 pascals. Okay, so that was part A. Part B is now imagining that we're going to take this block and we're going to rotate it so that this is now standing upwards, and this will now become my depth, and this will now become my breadth. So that's my B. Okay, so you can see now that the load, when I flip it around, will be coming from this direction here. So the load is now from here. You've got to imagine this thing being twisted and that the load is now on the sort of flat part. What's going to happen then? Well, one of the differences is that we keep the axes that we had before to identify them. So we've kept the XX, so my YY is now referring to the second moment of area, because it's bending in this plane, if you like, in this direction. So it's now IYY, we use the same formula, b times d to the power 3 divided by 12, but our values of b and d have now flipped, if you like. So b is, in the textbook they haven't flipped them. So b is now referring to 100, so that's my breadth. And my depth is now referring to 60 to the power 3. If you want, you could consider those fingers and then keep the same variables, which is what they've done in the textbook. Divide it by 12. And then when we work that value out, we're going to get 1.8 times 10 to the 6. So notice you're going to get 10 to 6. When you do these calculations, try to use the eng button on your calculator to get nice values like 10 to the 6, 10 to the 9 when you write out your final result. This will be millimeters to the power 4. So I'm going to rearranged the engineer's bending equation. So the stress, in y direction, is now going to be m over I times by y. So the m value doesn't change. It's still going to be 5,000. My I value has now got smaller. Notice that. Okay. So people have now gone to bed. 1.8 times 10 to the 6. And again, don't forget to convert this into meters to the power 4. So we need to times it by 1 times 10 to the minus 12. Okay, now the y distance for this formula is going to be the distance away from the load. This is in effect my neutral axis, so I need to measure this distance from here to here. So that's going to be 30 times 10 to the minus 3. And that will give me a result of 83.33 times 10 to the 6 pascals. So you can see that by having it on the green side, as it were, having it on the flat side, that you're going to get not double the stress, but knocking on to double the stress than compared to if you orientated it such that it was the longer side was standing up proud, as it were. Okay, so that's all I wanted to say about that example. As I said, in the example they're talking about sexual modulus. It's not really a term we need to concern ourselves with. That's something that you would tend to look up in engineering textbooks, where you are looking for maximum stresses in girders and things like that. So they tend to have in handbooks the sectional modulus as an expression where we're combining the maximum y and the I values together. Okay, so that's called sectional modulus. So that's going to be given z equals I over y. So that's taking into account the stiffness of the beam and also how far away it is, because the further away it is, it's going to therefore lead to naturally higher stress. So it's combine those two effects together. The second moment of area is the one that's going to win out. If you're going to have a high second moment of area, then that's potentially that's going to be the one that's really going to lead most likely to a stiff beam.